Imagine standing on a beach at night, looking up at the stars. Each one seems permanent, unchanging, tiny diamonds fixed in the cosmic tapestry. What if I told you that right now, somewhere in our galaxy, two of these seemingly immovable objects are hurtling toward each other at unimaginable speeds? What if I told you that when they meet, the energy released would outshine entire galaxies, forge the heaviest elements in existence, and send ripples through the very fabric of spacetime? You might think stellar collisions are rare cosmic accidents, but the truth is far more astonishing. Our universe is a celestial ballroom where stars are constantly dancing, sometimes gracefully orbiting for billions of years, and occasionally, catastrophically, merging in events so violent they transform not just themselves but the cosmos around them. In 2017, scientists detected something remarkable: gravitational waves from two neutron stars spiraling into each other 130 million light-years away. The collision lasted barely 2 minutes in our detectors, but in that fleeting moment, it answered questions that had puzzled humanity for generations. Where does gold come from? How do gamma-ray bursts work? Can we actually hear the universe? This was not just another astronomical observation. It was the beginning of a new era in our understanding of cosmic violence and creation. Tonight, we will journey into the heart of these stellar catastrophes. We will witness neutron stars with masses greater than our sun compressed into spheres the size of cities, whirling around each other hundreds of times per second before their final, cataclysmic embrace. We will see white dwarfs, the cooling corpses of once mighty stars, reigniting in thermonuclear fury when they collide. And we will explore how the largest stars in existence can merge to form monsters that eventually collapse into the black holes that haunt our universe. What really happens when stars collide? The answer will change how you look at the night sky forever. Dr. Valentin Zhukov still remembers the first time he truly saw the stars. Not the faint speckles visible from his childhood home in Moscow, but the overwhelming cosmic panorama that greeted him during a research trip to Chile's Atacama Desert. It was like seeing the ocean for the first time, he tells me, his eyes still widening at the memory. You realize how small you are, but also how connected to something immense. As an astrophysicist at the Gravitational Wave Observatory, Zhukov has spent 20 years studying what most of us never witness: stars in their death throes, their catastrophic endings, and their violent rebirths through collision. For most of human history, we believed stars were eternal and unchanging, fixed lights guiding sailors and nomads across endless journeys. Even when we realized stars had lifespans, born in nebulae, burning for billions of years, then dying in supernovae or cooling into white dwarfs, we still thought of them as solitary travelers. The truth is far more dynamic. Our galaxy contains over 100 billion stars, and more than half exist in binary systems, two stars orbiting each other in an eternal cosmic dance. Some triple systems exist, even rare quadruple arrangements. This stellar togetherness isn't just common. It's crucial to understanding the universe's most energetic events. Imagine the Earth and Moon, Zhukov explains, sketching quickly on a notepad. Now replace both with stars, but keep them just as close proportionally. He draws two circles nearly touching. Their gravitational pull on each other creates extraordinary conditions: tidal forces, mass transfer, and eventually, for many systems, collision. The concept seems straightforward, but the scales involved defy comprehension. Our Sun has a mass 333,000 times that of Earth, with a core temperature of 15 million degrees Celsius. Now imagine two such behemoths spiraling toward each other. The journey toward stellar collision begins billions of years before the actual event. Most stars form together from the same cloud of gas and dust, born as twins or triplets, already bound by gravity. Their fates become intertwined from birth, but the nature of their eventual encounter depends entirely on what kind of stars they become. Stars like our Sun live relatively peaceful lives for about 10 billion years, fusing hydrogen into helium in their cores. Larger stars burn faster and die younger, while smaller stars can smolder for trillions of years. This diversity creates multiple collision scenarios, each with distinctive consequences for the universe. We've categorized stellar collisions into major types, explains Dr. Zadie Ochoa, Zhukov's colleague and specialist in computational astrophysics. Neutron star mergers, white dwarf collisions, main sequence mergers, and various combinations of these with black holes. Each writes its own unique story in the cosmos. But how do we actually observe these cosmic train wrecks happening in distant space? Until recently, we couldn't. Stars might collide millions of light-years away, the events hidden by dust clouds or simply too far to see clearly. This changed dramatically in 2015 with a discovery that would transform astronomy forever. September 14, 2015. Ochoa says, the date clearly etched in her memory. The first direct detection of gravitational waves from two black holes merging. Not stars exactly, but their remnants. It proved Einstein right and gave us an entirely new way to observe the universe. Not through light, but through ripples in space-time itself. This breakthrough would soon lead us to actually witnessing what happens when stars collide. But to understand the significance of what we discovered, we first need to grasp what these stars actually are, how they evolve, and the cosmic circumstances that lead to their violent reunions. As Zhukov puts it, to appreciate the collision, you must first know the colliders. Imagine condensing the 13.8 billion year history of our universe into a single Earth year. In this cosmic calendar, the Big Bang occurs on January 1st, and our Sun and solar system don't form until early September. The first multicellular life on Earth appears in late November. Dinosaurs roam from December 24th to 28th. And all of recorded human history occupies merely the last minute of December 31st. In this context, even the longest-lived stars, the tiny red dwarfs that can burn for trillions of years, are temporary. The most massive stars, hundreds of times larger than our Sun, exhaust their fuel in cosmic eye blinks, sometimes just a few million years, barely a day in our cosmic year. Stars are essentially nuclear fusion reactors held together by gravity, explains Professor Vincent Zachariah, director of the Stellar Evolution Project at Harvard. Their entire existence is a battle between these two forces. Gravity pulling inward, fusion pushing outward. The story begins with vast clouds of hydrogen gas. Slight density variations cause certain regions to contract under their own gravity. As the gas compresses, it heats up, eventually reaching the critical temperature. Approximately 10 million degrees Celsius, where hydrogen nuclei overcome their mutual repulsion and fuse into helium, releasing enormous energy. This nuclear fusion ignites the star, creating the pressure that counterbalances gravity. For stars like our Sun, this hydrogen fusion in the core will continue for about 10 billion years in a phase astronomers call the main sequence, the stable, middle-aged period of a star's life. But stars are born with different masses, and this initial mass determines their entire life story. Mass is destiny for stars, says Zachariah. A star 10 times more massive than our Sun burns through its hydrogen thousands of times faster. It's like comparing a gas-sipping economy car to a fuel-guzzling rocket. When main sequence stars exhaust the hydrogen in their cores, their evolution diverges dramatically based on mass. Our Sun will swell into a red giant, eventually shedding its outer layers to form a planetary nebula, while its core contracts into a white dwarf, a hot, dense ember roughly the size of Earth that will cool over trillions of years. Stars between 8 and 20 times the Sun's mass face more violent ends. Once nuclear fusion can no longer counteract gravity, their cores collapse catastrophically, creating a supernova explosion. The incredible pressures during collapse compress the core into a neutron star, an object with more mass than our Sun squeezed into a sphere just 20 kilometers across. The density of neutron stars defies comprehension. A sugar cube-sized piece would weigh about 1 billion tons on Earth. Their surfaces are smoother than anything on Earth, with mountains perhaps 1 millimeter high. They spin incredibly fast, up to hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. For stars exceeding 20 solar masses, even the resistance of neutrons cannot halt the collapse. These behemoths form black holes, regions where gravity is so intense that nothing, not even light, can escape. But here's where it gets interesting, Zachariah continues, leaning forward in his chair. Most stars aren't loners. They're born in pairs or groups, already locked in gravitational relationships. And this changes everything about their fates. In binary systems, stars influence each other's evolution in profound ways. If they're close enough, the larger star can actually pull material from its companion as it expands into a red giant. This vampire behavior accelerates its evolution while altering its partner's development. Even more dramatically, as stars age into compact objects like white dwarfs or neutron stars, their orbits can decay through various mechanisms, leading to the ultimate stellar encounter, collision. We used to think stellar collisions were rare cosmic accidents, says Dr. Ochoa. Now we understand they're part of the cosmic life cycle, as natural as supernovas or planetary nebulae, just happening on longer timescales. And here lies the first great mystery that stellar collisions help solve: the origin of the heaviest elements in our universe. Open your hand and look at your wedding ring, your watch, or any gold jewelry you might be wearing. Where did that gold come from? Until 2017, astronomers had theories but no definitive answer. Now we know. The gold adorning human bodies across our planet was forged in the fiery collision of neutron stars billions of years ago. This revelation represents one of the most profound connections between stellar collisions and our daily existence. To understand it, we need to explore how elements form in the universe. The Big Bang produced only the lightest elements, mainly hydrogen and helium with traces of lithium. Everything heavier, from the carbon in our bodies to the oxygen we breathe, had to be manufactured inside stars through nuclear fusion. As ordinary stars fuse hydrogen into helium, they gradually create heavier elements: carbon, oxygen, neon, silicon, up to iron. But iron presents a problem. Fusing elements lighter than iron releases energy, but creating anything heavier than iron requires energy. This is why iron accumulation in a star's core triggers collapse and supernova. For decades, astronomers believed supernovae were responsible for creating all elements heavier than iron, including gold, platinum, uranium, and lead. But detailed models showed a problem. Supernovae couldn't account for the abundance of these heaviest elements we observe in the universe. Something was missing from our understanding, explains Dr. Elena Cortez, nuclear astrophysicist at Los Alamos National Laboratory. Supernovae create heavy elements through what we call the R process, rapid neutron capture, but our models showed they couldn't produce enough of certain elements, particularly gold and platinum. The answer, it turned out, was hiding in one of the most violent events in the universe: neutron star collisions. When two neutron stars spiral toward each other, they create a cosmic environment unlike anything else. These stars contain matter compressed to densities greater than an atomic nucleus, with a teaspoon weighing billions of tons. Their collision releases neutron-rich material into space under extraordinary conditions, temperatures reaching 100 billion degrees and densities millions of times greater than Earth's core. This creates the perfect environment for the R process, Cortez continues. Neutrons rapidly bombard atomic nuclei, building heavier and heavier elements before the nuclei have time to decay. In mere seconds, elements from zinc to uranium form in abundance. The confirmation came dramatically on August 17, 2017. Gravitational wave detectors LIGO and Virgo registered waves from what analysis revealed to be two neutron stars spiraling together. Astronomers quickly pointed telescopes toward the source and captured something extraordinary: a kilonova, the optical flash from a neutron star collision. The spectroscopic signature was unmistakable. Zhukov recalls with evident excitement. We were watching heavy elements being synthesized in real time. Gold, platinum, uranium, all the elements that supernovae models couldn't adequately explain, were being created before our eyes, 130 million light-years away. The amount of heavy elements produced was staggering. That single collision created somewhere between 3 and 13 Earth masses of gold, millions of times more than all gold ever mined on our planet. Similar amounts of platinum, uranium, and other heavy elements were also forged. Every piece of gold jewelry on Earth was once part of a neutron star, Ochoa notes. The gold in your wedding ring was created in a stellar collision that happened before our solar system formed. The heavy elements scattered through space, eventually incorporated into the cloud that formed our sun and planets. This cosmic alchemy isn't limited to neutron star collisions. Different types of stellar mergers create different elements and energetic phenomena. When white dwarfs, the dense remnants of sun-like stars, collide, they can trigger runaway nuclear fusion, creating a distinctive class of supernova called Type Ia. These explosions produce large quantities of iron and distribute it throughout their galaxies. Main sequence stars merging create different phenomena. When two sun-like stars collide, they can form a more massive, rapidly rotating star with unusual properties. If a main sequence star collides with a red giant, it can create what astronomers call a blue straggler, a star that appears younger than its neighbors because the collision rejuvenated it with fresh hydrogen. But perhaps the most mysterious collisions involve black holes. While not technically stars anymore, these collapsed stellar remnants can merge with neutron stars or other black holes, creating the most energetic events detected through gravitational waves. Black hole mergers don't create new elements. They're too dense for any material to escape, explains Zhukov. But they release enormous energy through gravitational waves, the equivalent of converting multiple solar masses into pure energy, exceeding the combined light output of all stars in the observable universe for a brief moment. The diversity of stellar collisions provides a cosmic laboratory for extreme physics impossible to replicate on Earth. But what actually happens in the moments before, during, and after these cosmic crashes? How do stars that have orbited peacefully for billions of years suddenly find themselves on a collision course? To understand this, we need to explore the celestial mechanics that bring stars together, and the remarkable methods astronomers have developed to detect these events across the vast distances of space. 13,000 years ago, when humans were painting on cave walls and the last ice age was ending, two neutron stars began the final phase of their cosmic dance in a galaxy far from our own. After orbiting each other for millions of years, the inexorable force of gravity had brought them closer with each passing millennium. In their final minutes, these city-sized stellar corpses, each weighing more than our sun, were separated by just a few hundred kilometers, orbiting each other hundreds of times per second, warping spacetime around them like massive ships creating waves in water. They generated gravitational ripples that spread outward at light speed. On August 17, 2017, those ripples finally washed over Earth, causing LIGO's laser interferometers to detect a characteristic chirp signal, a rapid increase in frequency and amplitude that lasted approximately 100 seconds. Scientists knew immediately they were witnessing something unprecedented. The first detected neutron star merger. The signal was unmistakable, remembers Dr. Zhukov, who was among the first to analyze the data. Unlike black hole mergers, which typically last a fraction of a second in our detectors, this signal persisted and evolved exactly as our models predicted for neutron star in spiral. But what forces bring stellar objects to these catastrophic encounters? The journey toward collision typically begins with one critical mechanism: orbital decay. Stars or stellar remnants in binary systems don't maintain fixed orbits indefinitely. Several processes can cause orbits to shrink over time. The most significant is gravitational radiation, the the emission of energy through gravitational waves. Einstein's general relativity predicts that accelerating masses disturb spacetime, creating ripples that carry away orbital energy. It's like a very slow brake on the orbital motion, explains Dr. Ochoa. For objects like Earth orbiting the Sun, the effect is negligible, will never spiral into the Sun this way. But for compact objects like neutron stars orbiting each other at close range, the energy loss becomes significant. Other mechanisms can accelerate orbital decay. If ordinary stars orbit in a gas-rich environment, they experience drag forces. In triple-star systems, complex gravitational interactions can drive two stars toward collision. Even the influence of a passing star or gas cloud can disrupt stable orbits. The universe has patience, notes Zhukov. Processes that take billions of years are just part of cosmic evolution. What seems stable on human timescales may be in the midst of dramatic change on astronomical ones. As binary neutron stars spiral closer, their orbital period decreases while their speed increases. In the final minutes, relativistic effects become pronounced. The intense gravity creates gravitational lensing, where each neutron star's light bends around the other. Tidal forces begin distorting their shapes from perfect spheres into slight ovals pointed toward each other. At this stage, the neutron stars orbit hundreds of times per second, moving at nearly a third the speed of light. The gravitational waves they generate carry away energy equivalent to several solar masses, briefly outshining the gravitational wave output of all other sources in the observable universe combined. What happens next depends on the total mass of the system, says Ochoa. If the combined mass exceeds a critical threshold, about 2.5 to 3 solar masses, the collision will ultimately form a black hole. Below that threshold, it may form a massive neutron star. The actual collision occurs in milliseconds. When the neutron stars touch, their outer layers shred into a spiral pattern while their cores merge. The temperature reaches 100 billion degrees, about 6,000 times hotter than the Sun's core. Neutron-rich material is ejected at up to 30% the speed of light, expanding and cooling rapidly. This ejected material undergoes rapid neutron capture, our process, nucleosynthesis, creating heavy elements. As these newly formed elements undergo radioactive decay, they produce a distinctive flash called a kilonova, about 1,000 times brighter than a typical nova but still dimmer than a supernova. The 2017 event was revolutionary because we captured it with both gravitational wave detectors and conventional telescopes, says Zhukov. For the first time, we could directly connect gravitational wave astronomy with electromagnetic astronomy, seeing the same event through entirely different physical channels. Within seconds of detecting the gravitational wave signal, automated systems alerted observatories worldwide. The Fermi Space Telescope had already detected a gamma-ray burst from the same region just 1.7 seconds after the gravitational wave peak. Within hours, nearly 70 ground and space-based observatories were examining the event across the electromagnetic spectrum. What they witnessed was the radioactive glow of newly created heavy elements cooling and decaying, confirming decades of theoretical work about neutron star mergers and our process nucleosynthesis. The observations also helped solve a long-standing mystery about short gamma-ray bursts, which had been theoretically linked to neutron star mergers but never confirmed until this event. While neutron star collisions are spectacularly violent, they represent just one type of stellar merger. What happens when other types of stars collide follows different physical pathways, each with its own cosmic significance. Dr. Zadie Ochoa stands before an enormous digital display at the Stellar Collision Modeling Center. With a gesture, she brings up a simulation showing 2 white dwarf stars, each about the size of Earth but containing the mass of our Sun, spiraling toward each other. White dwarf collisions are fundamentally different from neutron star mergers, she explains. White dwarfs are supported by electron degeneracy pressure rather than neutron degeneracy. They're about 1,000,000 times less dense than neutron stars but still incredibly compressed by everyday standards. When white dwarfs collide, the outcome depends on their combined mass and the collision geometry. If their total mass exceeds 1.4 solar masses, the Chandrasekhar limit, the collision triggers runaway nuclear fusion, creating a Type Ia supernova that completely destroys both stars. The simulation shows the stars touching, then deforming from spheres into a chaotic, rapidly rotating mass. Suddenly, a thermonuclear shockwave erupts from the contact point, propagating through both stars in seconds. The entire system detonates in a blinding flash, leaving nothing behind but an expanding shell of debris rich in iron and other heavy elements. Type Ia supernovae are crucial cosmic tools. Ochoa continues. Their consistent intrinsic brightness makes them valuable standard candles for measuring cosmic distances. It was observations of distant Type Ia supernovae that led to the discovery of dark energy and the accelerating expansion of the universe. Not all white dwarf collisions end in complete destruction. Glancing collisions or mergers of lower-mass white dwarfs can create exotic objects called extreme helium stars, or our coronae borealis variables, rare stars with unusual chemical compositions and erratic brightness changes. Switching the display to another simulation, Ochoa shows two main sequence stars, actively fusing hydrogen like our Sun, on a collision course. Main sequence collisions typically occur in dense stellar environments like globular clusters, she explains. Unlike the compact remnants we've discussed, these are enormous diffuse objects. When they collide, it's initially more like gas clouds merging than solid objects impacting. The simulation shows the star's outer atmospheres interacting first, creating shock waves and turbulence. As their cores approach, tidal forces distort both stars. The actual merger creates a single, larger star that oscillates violently before settling into a new equilibrium, rotating rapidly and often with unusual chemical abundances from the mixing of stellar materials. These mergers create a phenomenon we call blue stragglers. Zhukov adds, joining the presentation. In star clusters, we can estimate all stars' ages based on when the cluster formed. But blue stragglers appear younger and more massive than they should be. They're essentially rejuvenated by the fresh hydrogen from the collision. More exotic collisions involve interactions between different stellar types. When a compact object like a neutron star plunges into a red giant's extended atmosphere, it spirals through increasingly dense layers toward the core. This common envelope phase can end with either orbital stabilization or complete merger, often ejecting the giant's outer layers as a nebula. Perhaps the most dramatic stellar encounters involve black holes. While technically no longer stars, these collapsed stellar remnants play crucial roles in cosmic evolution. When a neutron star meets a black hole, it's not so much a collision as a consumption, Zhukov explains, bringing up a new simulation. Tidal forces from the black hole literally tear the neutron star apart before it crosses the event horizon. The simulation shows a neutron star approaching a black hole 10 times its mass. As it nears, the neutron star stretches into an elongated shape. Suddenly, it ruptures, with part of its matter forming a spiral pattern as it falls into the black hole while some material is ejected at tremendous speeds. These events create gravitational waves with distinctive patterns and potentially electromagnetic counterparts from the disrupted neutron star material, says Ochoa. LIGO has likely detected several such events already. When two black holes collide, the event is invisible to conventional telescopes. Black holes emit no light, but creates enormous gravitational wave signatures. The first detection of gravitational waves in 2015 came from two black holes of 29 and 36 solar masses merging to form a single 62 solar mass black hole, with 3 solar masses converted to gravitational wave energy. The variety of stellar collisions forms a complete tapestry of cosmic violence and creation, Zhukov notes. From the heavy elements in our jewelry to the iron in our blood, from the energy patterns we detect with our most sophisticated instruments to the fundamental questions about physics, stellar collisions touch every aspect of our understanding of the universe. But detecting and studying these events requires technological innovations that themselves represent triumphs of human ingenuity. How do we actually observe phenomena occurring millions or billions of light-years away, often hidden by dust clouds and visible only for brief moments? Dr. Vincent Zachariah still remembers the morning of February 11, 2016. He was in a packed auditorium at the National Press Club in Washington, D.C., as the LIGO scientific collaboration announced the first direct detection of gravitational waves. The room erupted in applause when the signature chirp was played, the sound of two black holes merging 1.3 billion light-years away, their gravitational waves converted to audible frequencies. It was like putting on cosmic headphones for the first time, Zachariah recalls. After centuries of looking at the universe, we could finally hear it. This breakthrough represented not just a confirmation of Einstein's century-old prediction, but the birth of an entirely new form of astronomy. For all of human history, we had studied the cosmos exclusively through electromagnetic radiation, visible light, radio waves, X-rays, and other forms of photons. Gravitational wave astronomy offered a fundamentally different window into the universe. Electromagnetic astronomy is like watching the universe, explains Zhukov. Gravitational wave astronomy is like feeling its pulse. The technology behind gravitational wave detection showcases extreme engineering. LIGO's twin detectors in Louisiana and Washington state use laser interferometry to measure infinitesimal distortions in spacetime. Each detector consists of two 4-kilometer-long vacuum tubes arranged in an L shape. Laser beams bounce between mirrors at the ends of these tubes, precisely measuring their separation distance. When gravitational waves pass through Earth, they subtly stretch and compress spacetime, changing the distance between the mirrors by a tiny fraction, typically less than the width of a proton. This change creates an interference pattern in the recombined laser beams, which scientists can analyze to determine the gravitational wave's properties. The precision is almost inconceivable, says Ochoa. We're measuring distances with accuracy comparable to detecting a human hair's width change in the distance between Earth and the nearest star. To achieve this sensitivity, LIGO must isolate its instruments from countless potential disturbances: seismic activity, traffic vibrations, ocean waves hitting distant shores, and even quantum fluctuations in the laser light itself. The mirrors hang from sophisticated multi-stage pendulums inside the world's largest vacuum chambers, equipped with active and passive dampening systems. The European Virgo detector near Pisa, Italy, uses similar technology, while Japan's Kagra detector adds the innovation of operating deep underground with cryogenically cooled mirrors to further reduce interference. Future detectors like LISA, Laser Interferometer Space Antenna, will operate in space, using 3 spacecraft millions of kilometers apart to detect lower-frequency gravitational waves from supermassive black hole mergers. Gravitational wave astronomy has revolutionized our ability to detect stellar collisions, says Zhukov. But we still need traditional telescopes to understand the full picture. When LIGO Virgo detects a potential neutron-star merger, automated systems immediately alert observatories worldwide. This multi-messenger astronomy, combining gravitational wave data with observations across the electromagnetic spectrum, provides complementary information about collision events. Gamma-ray telescopes like Fermi and Swift capture the initial high-energy burst, lasting mere seconds. Optical telescopes then track the kilonova's fading glow over days and weeks, while radio telescopes monitor the expanding shock wave for months or years. X-ray observations reveal the hot aftermath and potential formation of relativistic jets. The 2017 neutron-star merger was observed by over 70 observatories across every continent and in space, notes Ochoa. It was arguably the most extensively observed astronomical event in history. For stellar collisions not involving neutron stars or black holes, which don't produce strong gravitational waves, detection relies on different methods. Unusual light curves, unexpected chemical signatures, or stars with properties that don't match their apparent ages can all indicate past collision events. In star clusters, astronomers identify blue stragglers, stars that appear younger than their neighbors, as likely products of stellar mergers. The Milky Way contains numerous collision products visible to our telescopes, including rapidly rotating stars with unusual compositions. Perhaps the most spectacular collision products are rare objects called luminous red novae. These explosive events, brighter than ordinary novae but less luminous than supernovae, are believed to result from merging main sequence stars. The 2008 explosion V1309 Scorpii provided compelling evidence for this theory when pre-explosion data showed a contact binary system with a rapidly decreasing orbital period before it erupted as a red nova. We're developing increasingly sophisticated ways to detect collision events and their aftermath, says Zachariah. Machine learning algorithms now continuously scan sky survey data, identifying anomalous objects for further investigation. Computer simulations help us interpret observations by modeling physics too complex for analytical solutions. These detection methods have revealed that stellar collisions are not rare cosmic accidents but integral parts of galactic evolution. In dense environments like globular clusters, stellar collisions occur regularly on astronomical timescales. Even in less crowded regions, binary star evolution naturally leads to mergers through various mechanisms. The technological innovations driving collision astronomy extend beyond detection to analysis. Supercomputer simulations incorporating relativistic hydrodynamics, nuclear physics, neutrino transport, and magnetohydrodynamics help scientists model collision processes in unprecedented detail. The computation requirements are staggering, notes Ochoa. Simulating just a few milliseconds of a neutron-star merger can require millions of CPU hours on the world's most powerful supercomputers. We're essentially creating virtual laboratories for physics under conditions impossible to replicate on Earth. As detection technology improves, we're discovering stellar collisions at increasing rates. LIGO Virgo's third observing run detected dozens of compact object mergers, including several potential neutron-star black hole mergers. Future upgrades promise even greater sensitivity, potentially observing multiple collision events weekly. Space-based gravitational wave observatories like LISA will extend detection capabilities to new frequency ranges, potentially observing tens of thousands of white dwarf binaries within our galaxy and dozens of supermassive black hole mergers annually across cosmic history. We've entered a golden age of collision astronomy, says Zhukov. Each new detection adds another piece to our understanding of these extreme cosmic events. But beyond their astrophysical significance, stellar collisions hold profound implications for our existence and our place in the cosmic story. These violent encounters forge the chemical elements essential for life and shape the evolution of galaxies themselves. Dr. Elena Cortez carefully places a gold ring on the laboratory table next to a vial of iron filings. The universe had to destroy stars to create these materials, she says. The gold in this ring required the collision of neutron stars. The iron needed a supernova explosion. Both represent cosmic violence transformed into the building blocks of worlds and life. This transformation, from stellar catastrophe to the essential ingredients of planets and organisms, represents one of the most profound implications of stellar collisions. The heavy elements created in these violent events don't simply disperse into empty space. They become incorporated into new generations of stars and planets. Our solar system formed from a molecular cloud already enriched by previous stellar generations, including the debris of ancient collisions. Spectroscopic analysis reveals that Earth contains elements from multiple stellar sources: iron and nickel from supernovae, gold, platinum, and other heavy elements from neutron star mergers, carbon and oxygen from the normal evolution and death of earlier stars. We are literally made of stellar remains, notes Zhukov. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were forged in stars that died before our sun was born. and the heaviest elements in our bodies required the most extreme stellar encounters. This cosmic recycling operates continuously throughout galactic history. Each generation of stars incorporates material from previous generations, gradually increasing the abundance of heavy elements. Astronomers call this process chemical evolution, and it's directly observable in the composition of stars formed at different cosmic epochs. The oldest stars we've found contain almost no elements heavier than hydrogen and helium, explains Ochoa. Stars forming today, like our Sun, have much higher metallicity, astronomical jargon for the abundance of elements heavier than helium. This enrichment happens largely through supernovae and stellar collisions. The implications extend beyond chemistry to the very structure of galaxies. When massive stars collide, they can form even more massive stars that eventually produce black holes. These black holes may themselves merge, creating increasingly massive black holes that influence galactic dynamics through their powerful gravitational fields. At the extreme end, supermassive black holes, millions or billions of times more massive than our Sun, lie at the centers of most large galaxies, including our Milky Way. While these behemoths likely grew primarily by accreting gas and stars, hierarchical mergers of smaller black holes contributed to their evolution. Stellar collisions leave fingerprints on cosmic structure across all scales, says Zachariah. From the chemical composition of individual planets to the distribution of stars within galaxies to the growth of the supermassive black holes that regulate galactic evolution. The collisions also impact the formation of planetary systems. Binary star mergers can disrupt existing planetary orbits or create conditions for new planet formation. Some evidence suggests that unusual planetary systems may result from stars that merged before or during planet formation. Even Earth may bear the influence of stellar collisions beyond just its chemical makeup. The heavy bombardment period early in our solar system's history, when numerous asteroids and comets struck the young planets, might have been triggered by gravitational disturbances from passing stars, potentially including merger products with unusual trajectories. On the grandest scales, stellar collisions influence cosmic timekeeping itself. Type Ia supernovae, many resulting from white dwarf mergers, serve as standard candles for measuring cosmic distances due to their consistent intrinsic brightness. These measurements led to the discovery that the universe's expansion is accelerating, implying the existence of dark energy and fundamentally changing our understanding of cosmic fate. It's remarkable that we can use the light from stellar collisions to measure the universe's expansion rate and determine its ultimate destiny, notes Zhukov. The violence of merging stars becomes a cosmic yardstick. Beyond their astrophysical implications, stellar collisions push the boundaries of fundamental physics. The extreme conditions they create, temperatures in the billions of degrees, densities exceeding nuclear matter, magnetic fields trillions of times stronger than Earth's, cannot be replicated in terrestrial laboratories. They serve as natural experiments testing physics under the most extreme conditions imaginable. Neutron star mergers, in particular, probe the behavior of matter at densities we can't create on Earth, explains Cortez. The equation of state of nuclear matter, how it responds to pressure at various densities, remains incompletely understood. Each merger observation helps constrain theoretical models. Gravitational waves from these events also test general relativity under strong field conditions. So far, Einstein's century-old theory has passed every test, but scientists continue searching for potential deviations that might point toward quantum gravity or modified gravity theories. We're using stellar collisions to probe the fundamental nature of spacetime itself, says Ochoa. The ripples from these distant catastrophes carry information not just about the collision but about the very fabric of reality. Perhaps most profoundly, stellar collisions embody the universe's endless cycle of destruction and creation. Violence becomes genesis. Ending becomes beginning. The death spiral of binary neutron stars creates the gold in wedding rings, symbols of eternal union. The catastrophic merger of white dwarfs forges iron, the element at the core of hemoglobin that carries oxygen through our bodies. There's poetry in this cosmic recycling, reflects Zachariah. Nothing in the universe is truly destroyed. It's transformed, incorporated, repurposed. Even the most violent events create the conditions for new possibilities. As our detection capabilities improve, we continue discovering new collision types and unexpected phenomena. The universe reveals itself as more dynamic, more violent, and more interconnected than we ever imagined. Each collision observation adds another thread to the cosmic tapestry, helping us understand not just distant stars but our own origins and future. The Arizona night is clear and cold as Dr. Valentin Zhukov adjusts the University Observatory's telescope. A group of undergraduates clusters around him, their faces illuminated by the soft red glow of safety lights designed to preserve night vision. Tonight we're observing T. Coronii Borealis, Zhukov tells them. It's a recurrent nova, a white dwarf pulling material from a companion red giant. Not a collision yet, but a system that showcases the interconnected fates of stars in binary relationships. As the students take turns at the eyepiece, Zhukov reflects on how studying stellar collisions has changed his perspective on existence itself. After 20 years observing the most violent events in the cosmos, he finds himself contemplating not just astrophysics but philosophy. Stellar collisions teach us profound lessons about impermanence, he says quietly. Stars that appear eternal on human timescales are actually in constant flux, orbiting, evolving, sometimes merging in spectacular fashion. The cosmos is not static but dynamic, a continuous dance of matter and energy, destruction and creation. This cosmic perspective, seeing ourselves as participants in an ongoing universal story, transforms how we understand our place in existence. The heavy elements in our bodies and our planet were forged in stellar furnaces and catastrophic collisions billions of years before Earth formed. The gold in our jewelry, the platinum in our catalytic converters, the iodine in our thyroid glands, all required neutron star mergers to exist. We are, quite literally, made of star stuff, Zhukov continues, echoing Carl Sagan's famous phrase. But more specifically, we're partially made from the debris of stellar collisions. Our very existence depends on cosmic violence that occurred long before our sun ignited. Dr. Zadie Ochoa expresses a similar sentiment when discussing the broader implications of her work. Studying these extreme events gives me a strange sense of connection to the universe, she explains. The boundary between out there and right here dissolves when you realize the atoms in your body have this cosmic history. This perspective also highlights time's vast scales. The stellar collisions we observe today occurred millions or billions of years ago, their light and gravitational waves only now reaching Earth. The heavy elements created in ancient neutron star mergers drifted through interstellar space for eons before becoming incorporated into our solar system. We're not just observers of cosmic history, we're its products, notes Ochoa. And the processes we study, stellar evolution, collision, element formation, continue throughout the universe, creating the conditions for future generations of stars, planets, and potentially life. The story of stellar collisions also reveals the universe's interconnectedness. Stars influence each other gravitationally, chemically, and through radiation. Their interactions and occasional mergers shape galactic evolution, element distribution, and ultimately the conditions for life itself. Nothing in the cosmos exists in isolation, Zhukov tells his students. Just as these binary stars affect each other's destiny, everything in the universe exists in relationship. Galaxies, stars, planets, and living beings. The gravitational waves from a distant neutron star merger pass through all of us, subtly stretching and compressing our atoms by less than the width of a proton. Perhaps most significantly, stellar collisions embody the universe's fundamental pattern: transformation rather than creation or destruction. Matter and energy change forms but remain part of the cosmic tapestry. The catastrophic end of two stars becomes the beginning of something new: heavy elements, electromagnetic radiation, gravitational waves, and eventually, new stars and planets from the enriched material. The universe doesn't waste anything, Ochoa observes. Even the most destructive events serve creation in the grand scheme. The gold atoms in my wedding ring witnessed the violent death of neutron stars billions of years ago. Now they're part of a symbol of human connection and commitment. This pattern of transformation extends to knowledge itself. Each new stellar collision observation transforms our understanding, revealing unexpected phenomena and challenging theoretical models. The first detection of gravitational waves from merging black holes fundamentally changed astronomy, opening an entirely new window on the cosmos. Science progresses through transformation too, notes Zachariah. New observations don't just add information. They reshape our conceptual frameworks. The 2017 neutron-star merger didn't just confirm existing theories about R-process nucleosynthesis and kilinovae. It transformed our understanding of how these processes work and their cosmic importance. As detection technology improves, we continue discovering new forms of stellar interactions and collision phenomena. Each discovery reveals the universe as more complex, more interconnected, and more beautiful than we previously understood. Back at the Arizona Observatory, a student looks up from the eyepiece with wonder in her eyes. "It's incredible to think that star system might eventually merge," she says, "and that similar mergers created the elements that make up our planet and our bodies." Zhukov smiles. "That's the most profound insight of stellar collision astronomy," he replies. "Not just understanding distant cosmic violence, but recognizing our intimate connection to it. We aren't separate from the processes we study. We're their outcome and their witnesses." As the night deepens and more students take their turns at the telescope, Zhukov gazes upward at the starry vault. Somewhere out there, neutron stars are spiraling toward each other, white dwarfs are accreting material from companions, and main sequence stars are transferring mass in intricate gravitational dances. Each system tells part of a cosmic story that ultimately includes us, observers made of star stuff, contemplating our stellar origins through instruments built from elements forged in ancient stellar catastrophes. "The stars do not just shine above us," Zhukov says softly to himself. "They shine within us." As we have journeyed through the violent beauty of stellar collisions, from the spiraling death dance of neutron stars to the thermonuclear fury of merging white dwarfs, from the alchemical forging of gold to the ripples in space-time that carry news of distant catastrophes, one truth emerges. We exist because stars collide. The gold in wedding bands, the platinum in laboratory equipment, the iodine essential for human health, all required neutron stars to merge billions of years before our planet formed. The iron in our blood and the calcium in our bones emerged from supernovae, some triggered by stellar collisions. The very atoms that form our bodies and our world bear witness to cosmic violence we are only now learning to detect and understand. This connection transcends the merely chemical. The gravitational waves generated by colliding stars and their remnants pass through our bodies, subtly stretching and compressing the space we occupy by infinitesimal amounts. When we detect these waves with our instruments, we are not simply observing distant phenomena. We are feeling the pulse of the cosmos itself, vibrations in the universal web that connects all matter. With each new collision detection, we refine our understanding of fundamental physics, cosmic evolution, and our place within the great unfolding story of the universe. We learn that destruction and creation are not opposites but aspects of transformation, that endings enable beginnings, that violence precedes genesis, that stars must die so that life might eventually exist. Perhaps this is why stellar collisions fascinate us beyond their scientific significance. They embody the profound pattern of cosmic renewal that permeates existence at all scales. They remind us that impermanence is not a flaw in the universe but its essential nature, the very quality that allows complexity and novelty to emerge from simpler beginnings. As we gaze at the night sky, we now understand that the seemingly fixed stars are engaged in a grand, slow-motion ballet, some destined to merge in spectacular displays of cosmic fireworks. And we recognize that the light reaching our eyes has traversed vast distances and times to tell its story, the ongoing epic of a universe continuously transforming itself. In the words of Dr. Valentin Zhukov, we study stellar collisions not just to understand distant violence, but to comprehend our deepest origins and connections. We are the universe becoming conscious of itself, star stuff contemplating the stars. When stars collide, they write their stories in light, in gravitational waves, and in the very elements that form new worlds. And when those worlds eventually produce beings capable of looking upward with wonder and inquiry, the cosmic story achieves something remarkable. It becomes known to itself. In the violent embrace of colliding stars, we find not alien catastrophes but the distant echoes of our own creation.